So how is everybody doing today? Everybody in a good spirit, all rested up? Because this is going to be a boring 3.5 hours. So and either you guys are going to try to keep me awake, or I have to keep you guys awake. One way or the other, we will manage to hang in there. And my name is Narendra Bedi. It's like a surrender. It's Narendra. It's easy to remember. And I've been with the company for 18 years doing pipe stress analysis. And now my title is what they call, I forget sometimes, Manager Technical Support. And I learned this trade going to Cal Poly Pomona. I was a graduate in 1970. So at least it was a good college at that time. I don't know now. I haven't been back there. So, and my colleague John Wong, he'll be on the keys, helping me. He did a wonderful job putting this PowerPoint presentation. Boy, I was scared. How the heck I'm going to put all these pages together? He did a very good job putting that together. And John graduated from UCLA. So we've been in this business for a while. So how much we can teach, I don't know, but we're going to try to walk you guys through a little bit of everything. So if you stay awake, you may think, hey, hell, I'm going to be a stress person. I know everything now. Because we're going to start from the ABC all the way to the most sophisticated software we have. So we're going to touch a little bit of everything here. And don't worry about taking too many notes, because all these sheets, everything is on the iDrive. So you all probably know that you can print the full-size slides from there. Okay? So now, how many of you even heard of this term pipe stress? I know Corey heard a lot of that scream and yell all the time. We always going at each other. So there are not too many. I'm not surprised, because this is not the mainstream subject. A lot of people don't know about this. And when I graduated, got my first job with Fluor, I have no clue what the T is and what the elbow is, So it was totally different. And so you guys will find out everything about those little gadgets we use. And, so we'll make it interesting one way or the other. But I bet you all know what the stress is. I bet every one of you knows. Every girlfriend, every boyfriend give out stress to everybody, right? so we know that what the stress means. And basically we can apply the same scenario for pipe stress. It's exactly the same. What stress means is any time you don't want to do something, or you don't like something, or somebody forcing you to do something, what do? You get stressed out. Anytime my dad says, hey, you can't go out tonight, you are up, messed up, how can I go? You're all pissed and kicking the table. So same way as the pipes here. We're going to be walking through the pipes today, knowing they're just like human beings. You heat them up, they go overstressed. You put somebody sit on them, they get overstressed. So it's the same scenario. If you think in those terms, what causes the stress, that's the reason we call it pipe stress, because somebody did not design it the way it should be. So it got overspanned, it got too hot. So that's what causes the pipe stress. And our group, which we call pipe stress group, literally looks like, hey, we create a stress. No, it's we take the stress out of the pipes. So what we try to do is keep the stress levels way down so that the systems don't damage anything and they don't break away. So now I'm going to go through the definition of pipe stress. It's a definition of pipe stress. Actually, it is a pipe stress analysis. I forgot to add the letter at the end, analysis. So if we look at that slide there, it's a pipe stress analysis is a process of evaluating the structural integrity of a given piping system within the guidelines established by applicable codes and standards of the particular industry. What that means is that all the piping systems go into the refineries, go into the nuclear power plants, go into the chemical plants, any power plant, any process plants, the piping has to meet some criteria. And those criteria are set by the ASME code, API code. Most of you probably know ASME means American American Association of Mechanical Engineers. So in order to qualify any system, you have to meet those codes. Okay? So that's the definition of that, but here is to design the systems so that they can have their full lifespan, which is in the refineries used to be 40 years. And I've seen they're still hanging there 60 years, even they are rotten and corroded and kicked around, but they still hang in there because somebody did a good job in designing them. What we're going to do is I'm going to break that whole session into 3-4 sections, starting from, like I said, ABC of the pipes. And first, before that, I would like to explain the definition of the pipe stress engineer. The pipe stress engineer, what does he do? The definition is he's a fully qualified professional with piping, pipe stress analysis experience, and is proficient in the utilization of piping stress engineering theories and practices. What it is, he's like a specialist. That's why you all will not see in colleges somebody say, hey, you want to take a classes of piping analysis or something, because this is just a sidekick, a specialized field, and the only place you can really learn is working in the companies who deal with this kind of business. And the person does not have to be degreed. I hate to say that because, well, you know, we all went to school. What the heck, you know. But there are some folks who just learned by experience working in the company as designers or been there for a while. It's just a matter of taking interest in learning and doing it. So it's not mandatory you got to have a BS degree. But it does help now. The clients are looking more and more degreed personnel with the PE stamp, so which we didn't have already before. Now, we're going back to this now. What are the responsibilities of a pipe stress engineer? There are quite a few things that you got to watch for, and it sounds pretty simple, but if we go through, you all will notice the one thing is we want to be careful that we are following all the codes, standards, and procedures, whatever are applicable to your systems. And we want to make sure the forces and moments we impose on the piece of equipment or in the steel structure, that it will not damage the pipe or the structure, or it will not mess up the equipment nozzles. So because all those nozzles on any piece of equipment, they are governed by certain codes. The ASME codes, the API codes. For the pumps, we got the API 610, you got to meet. For the tanks, you got a 650. For the air cooler, you have API 661. And for piping, you got B31.3 for chemical process piping. And they got a different one, which is more stringent, is for the nuclear power plants. called B31.1. So you got to make sure what kind of system you're dealing with, so you follow that particular code. And ensure that the stresses in the piping systems are within the allowables. Now you guys must be wondering, what is allowable? You know, allowables are based on the yield of the materials, but they are taken about 60, I think about 60, 2/3 of the yield gives you per the piping code, the allowable stress for that material. They're different. The allowables are different for each different material at a different temperature. So that's what you guys got to remember is for some could be 20,000 for the stainless steel with high temperatures. There could be only 7,000 psi. So those are set by the code. They're all published in the ASME B31.3 Appendix A. So you guys all have a copy. We'll go over that later. And so the piping is well supported. In other words, you got a pipe going to 300 feet or maybe going 1,000 feet. How you support that pipe? How adequately you're going to support it so it's not sagging, it's not buckling. So that got to keep in mind. The pipe will stay in place after installation. Go ahead, John. Go to the next one. Okay, that's what we're talking about, controlled deflections of piping systems due to the effect of thermal. That is just like the sagging. If you got too much sag in the middle of the pipe, pipes do deflect, even they look so stiff. But it doesn't matter what size it is. If you go 30, 40 feet of span, what you do is you get a right little dip in the middle. Between the two supports, it will get a little dip there. We try to avoid that. The stress engineers always look for that, because if you don't, the condensate in the lines could sit in there and corrode the pipes, or if it's too much sagging, it accumulate and create a problem with the slug flows under high pressure. It could push it through and hit the elbows, bends, and cause problems. So the deflections have to be carefully monitored. And for thermal, you got to watch it, because the fuel lines going together, if one is growing quite a bit, it's going to hit the next one. So the pipes has to stay in their place as they're designed. We got to watch for the deflections. And then the stress engineer is responsible for the special supports and strains. Now we'll go, these are the items, but we'll go later in the session see what those special items are. Those are which are not common and which are not standards. They need special attention for special purposes. So stress engineers, they design those supports. And any problems with the system or try to make it better, stress engineers, they work with the piping design group, whoever the designer is. They work with them so that the whole system will work adequately, and there won't be any problems. Okay, now that was the part was to make sure that things, the stress engineers have them. Now once you got everything and now you did your work, now you have to transmit the loads to other disciplines. You know, you did your work, you done the stress analysis, you're happy with it, but what are you going to do with it? Because you're done as a stress analyst, but somebody has to physically support these pipes. And that discipline is a structural group. So we pass on to them the loads on every location. Wherever pipe touches anything, that means there's action and there's back reaction. So you all probably heard about action equal to reaction. So if we are applying any force, imposing any force on any steel, it will see those loads. So we tabulate and provide structural group to design the steel to support it, and we pass on the loads on the equipment to the equipment group so they can check the integrity of the nozzles on the equipment. And rotating equipment, like the pumps, compressors, turbines, we give them the load so they can make sure that we are complying with the vendor requirements or the code requirements. If you exceed those numbers, what is allowed by the code, your warranties are not valid. So that's we got to be careful for those. And then what we do, finally we're done, we do the acquisitions for any sports, the special sports, and finally everything is done. Then we put all our books together with all the analysis shown from scratch to the end, final product. We do the documentation, put in the binders, and send it to the client for their use. Now we talked about piping systems. Now what is a piping system? Piping system is from one equipment to another, all the way through. Could be one drawing, could be 15 drawings, but it has to be a complete system from one end to another to make it work. We cannot stress analyze small portions of it because it has a continuous effect, thermal effect, and any kind of effects. You got to have a complete system. So here we see from the vessel column to the exchanger, we have complete system from nozzle to nozzle there. Good. Okay, this was all about the pipe stress analysis. This was all about pipe stress analyst responsibilities. But now we're going to get into the piping technology. Like I was telling you at the beginning, we're going to start from the ABC. So some of you already know, some may not. So it's just we'll touch a little base on that one. The components of piping, what makes all the piping system together. And here are some examples. On the left, we have an elbow. Okay. Now, elbows are used basically to make a turn. If the pipe is going straight, you don't need it. But hey, if you want to go from left to right or right to left, you have to turn. The elbow are used to make the turns. And then we have a T. T is to make the branch connections. You're going with the main runs, you want to break off to another side, we use the T's. And then we got the reducers. Reducers are just, it sounds like reducing it. You're going from one size to the next. You got a 10-inch line going, you want to say, hey, I need 6-inch from here on, so you put a reducer, 10 by 6, and you have the application of the reducer. Miscellaneous fitting, just like it shows, it can go 4 directions, any direction you want to go. So these are pretty common piping fittings. We call it piping fittings. And they could be all different sizes. Elbows could be same size in and out, or it could be reducing elbow or a reducing T. So it could be any sizes. And this, go here. So now, this is what we call the pipe. Probably everybody knows that this is the piping component. This is the main component. And the pipes are used to flow the fluids, from one place to another, from one equipment to another. So this looks like you got the pipes. This is how they are installed. They are piping systems. They are the elbows as we see them there. So this is here we've shown what the pipe looks like. Go ahead now. And there is that elbow. We're talking about making a turn. And T-branch, if you look, with my guy here, if you look here, there is a T here because this is a main header, and we're going to branch it off. This is called the T here. T and branch, because this is pretty much the same thing. We got T here and main headers. Go ahead. So these are the branch connections. See, when we go, the main headers are going from one building to another, and you want to branch off. This is what we call the branches of the main header. Okay. So the application of reducer, like we talked about, is right there. We are coming from bigger size, we reduce the size here. So that's the application of a reducer. Okay, now, this is the item, it's not always used for everything, but this is called insulation. Insulation is just like in winter people wear the warm clothes. If the lines are hard, you don't want to touch it. It can burn somebody. They insulate the lines with the high temperatures. Or they could be very cold to minus some degrees, minus 50 degrees. So they insulate them so they don't lose the heat. So the insulation of the pipes looks like this here. This is a, and the insulation could be, John, next one, John, yeah, go ahead one more. Same thing here, insulated pipe. This is a, at the North Slope, Prudhoe Bay, because temperatures are minus 40, minus 50. So this is how they insulate those lines. And here the some materials we use for the insulations. And the most commonly used is the calcium silicate and mineral wool, polyurethane, and a fiberglass. So this is the density given here for every one of them. This comes handy when you want to calculate the total weight of the system. So this is we calculate the weight on that using the density for that material. So now we have another component, which is the flanges. Now flanges are used to connect something. All the equipment, they come with the flanges. The pipe has to have its own flange so they can mate them, so they can put together the flanges, so they can bolt them together. And they are welded to the pipe, but they're bolted to any kind of fittings. Could be a valve, could be any kind of blinds in there, whatever. So this how this term is used. The flanges are on either end of the pipe. And now the between the flanges, there's always a gasket. You probably all know from other things you do in life. You know, any time you're trying to connect something, it always has a gasket. So gaskets and flanges goes together. And the stress engineers have to be very careful. They have to do a special stress analysis to see that there's no leakage. Because see, in the industry, when you're operating under high temperature, high pressure, the chances are they could leak. So stress engineers have to make sure under those conditions there won't be any leakage at the flanges. So these are different kind of flanges, slip-on, blind, angle, lap, socket weld, so different type of flanges. Go ahead. There's some more same thing. Most common ones are this one, raised face. These are mostly used, I would say, but 90% of the time in all the piping, raised face flanges are used. And now the flanges, the ratings are different. There are different ratings for different kind of pressures. When you hear somebody talking about what's the rating on the flanges, they could be 150 pound, 300 pounds, 600, 900, 1500. And the higher the rating, the higher is their capacity for the pressure. They can take higher pressure in the system, and they take higher loads because they get thicker and thicker. And all the flanges has to be built per the code too. Every component is in the piping system has to be qualified and manufactured per the codes. And our next component, probably you all know, these are the valves. And a valve is what is a valve? I mean, we all use it. We got it at home at the faucets. We got everywhere. But in our industry, we have different kind of valves to do different kind of functions. So we just go quickly through the different names. For the definition, a valve is a mechanical device that controls the flow of fluid and pressure within a system or a process. It just controls the flow. Okay? And there are different kind of, and what the functions of the valve. It stops and starts the flow. It can change the direction of the flow, or you can use to throttle or vary the fluid going through it. And they can control with the actuators the flow in the pipes. So now you guys would think, what's that has to do with the pipe stress? You are right. 50% of, I would say even 80% of stress engineers don't know the function, and including myself, I didn't know either, is what the functions are. But for the stress analyst or a stress engineer, you got to know the weight, how much that thing weighs. Because you can't do the stress analysis. It's like somebody with a 30-pound weight sitting up here, the child sitting on the table, somebody with 300-pound person sitting on the table. So that determines the stress level in that structure. So stress analyst has to know what the weight is, what the dimension is, and how to support it. Because some valves could be as heavy as 7, 8, 10,000 pounds. I mean, can you guys believe it? The giant's sitting up there, but 10,000 pounds, you have to figure out how to support them. Okay? So then there's a different kind of valve. There's a butterfly valve. This is the most skinnier and lightweight valve. And then we have the check valve. Check valve is another kind, but this is just tells you the fluid can go through one direction, it can't come back. So other valves, if you leave them open, it can go back and forth, but with the check valve, the fluid could go only one direction. Another kind we have is a ball valve, different kind, different construction. The next one is a glow valve. The different mechanisms. All these valves, what they do is it's a different combination of function it has. What you're trying to achieve with the flow of the process. You want to regulate it. You want to full boards. Some are good corrosive services, and so just depending on what kind of system you have, what you want to achieve. So you use different kind of valves there. So it's a glow valve the same way. Some has discs there, some disc kind of plugs in, some slides. The idea is to block them or regulate them. So glow valve. Now this one here tells us for the stress engineer or for the person just to looking at the name you can tell. It's the same size 12-inch valve. And it's a 300-pound class rating. For the same classification, same size, look at the difference in the weights. Our butterfly valve is only 218 pounds, whereas the glow valve weighs 1,745 pounds. So right away, when the stress analysts look at it, they worry about how to support the heavy ones. So we don't have to worry about the butterfly valve because it's only 218 pounds. Okay, so these were all the piping components. So everybody has a little bit of idea about what makes the piping system. All these components we went through, they combined and put together, it becomes a system. Piping system is nothing but a bunch of pipings connected with the different kind of components. Now we talked about the codes. This is very important to do the pipe stress analysis, which code to follow. And believe it or not, these codes are very extensive. They tell you how to do everything. If somebody get a chance to read the code, they tell you how to design everything and stay within those limits. And the first one we have is the B31.1. This is a power piping code, and that's we don't use here too much in Worley-Parsons in these offices here, because this is for the nuclear power plants and the boiler piping.